Welcome back. Today, we are diving into an absolute game changer for your software architecture. If you've ever found yourself totally lost in a tangled web of conditional statements, just trying to figure out exactly which part of your application is supposed to handle a specific request, well, you're in the right place. Today, we're mastering the chain of responsibility pattern. We're going to explore how this behavioral design pattern can help you write cleaner, way more scalable object-oriented code. Here is our roadmap for this explainer. We'll quickly introduce the pattern, see exactly how the chain works, break down its anatomy, explore some real-world applications, and finally, weigh the pros and cons. Let's jump right in.
Okay, Section 1, Introducing the Pattern, where it fits in the OOP universe. Because, before we use a new tool, we really need to know which toolbox it belongs in.
When we talk about classic object-oriented software design, we're usually referencing the famous Gang of Four patterns. And those are divided into three main camps. You've got your 5 creational patterns that deal with object creation and 7 structural patterns for object composition. But our focus today is on that third category. The chain of responsibility is one of the 11 behavioral patterns. Behavioral patterns are all about communication. They focus on how objects interact and, crucially, how they distribute responsibility among themselves. To really wrap our heads around this, let's map this highly technical software concept to something everyday, like a medical clinic. Picture a patient walking into a clinic. That patient represents our client request. Now, they don't just burst straight into the surgery room, right? First, they meet the receptionist. If the receptionist can handle the query, maybe it's just scheduling, it stops right there. If it requires medical triage, they pass it to the nurse. If the nurse can't resolve it, it goes to the doctor. Each staff member in this scenario is a handler. The patient literally just hands off their request to the start of the chain, and the clinic's internal structure routes it to the exact right person. Moving to Section 2, how the chain works, from messy code to elegant flows. Let's look at the exact software headache we're trying to cure here. If you've been coding for a while, this anti-pattern probably triggers your fight or flight response. We are looking at tightly coupled, nested try-catch operations. Operation A tries something, catches an exception, and explicitly calls Operation B. Then B catches an exception and explicitly calls Operation C. This is incredibly rigid. If you want to add a new step between B and C, you literally have to rewrite the core logic of B. The sender is hopelessly entangled with the receiver, making the whole codebase fragile and honestly a nightmare to maintain. So what's the fix? We replace that nested, hard-coded spaghetti with a clean, linear chain. Just look at the beautiful simplicity here. A request comes in and the sender simply hands it off to the first handler. That handler either processes it or says, "Not my job," and passes it to the next handler. The sender doesn't need to know if handler 1, 2, or 3 dealt with a request. It just knows it sent the request into the system. It's a true fire and forget mechanism. That is elegance in software design. So the crucial thing here is understanding the rules of this chain. When does the buck actually stop? Well, the processing chain naturally terminates in one of 2 exact scenarios. Scenario 1, a handler somewhere along the chain recognizes the request, has the right logic, and processes it completely. Boom, chain stops there. Scenario 2, the request is passed all the way down the line and you reach the end of the chain without any handler taking action. All right, Section 3, Anatomy of the Pattern. Diving into the UML architecture. Now that we've got the analogy down, it's time to roll up our sleeves and look under the hood. The absolute beating heart of this pattern is a concept called decoupling. We are explicitly avoiding coupling the sender of a request to its receiver. By chaining the receiving objects together, we give more than one object the opportunity to handle that incoming request. The sender is entirely liberated from needing to know the specific class or object that will execute the final behavior. Here's the base UML diagram that makes this magic happen. Over on the left, we have the client, which initiates the request. Notice how the line points only to the abstract handler class. The client has zero knowledge of the concrete handlers sitting below it. The abstract handler defines a common method, usually something like handle request, and holds a reference to the next handler in the chain. The concrete handlers, which inherit from that base handler, contain the actual business logic. If concrete handler 1 can't do the job, it just uses the base class's reference to pass the request right along to concrete handler 2. Let's ground that abstract UML with a highly practical example. We've got an interface here called iReceiver, and we have 2 concrete implementations of it, email error handler and fax error handler. We also have a message class containing a message priority, either normal or high. So an issue raiser sends a message to the first receiver.
If it's a normal priority, maybe the email handler processes it and we're done. But if it's a high priority, the email handler might pass it along the chain until it hits the fax handler to ensure it gets immediate physical attention. The logic dictating who handles what is perfectly encapsulated right within the handlers themselves. Section 4. Real-world applications. Where you see this in production. Let's zoom back out from the code for a second and look at where this pattern is actively working in the tools you interact with every single day. The chain of responsibility is literally everywhere in modern software. Think about your email spam detector. An incoming email is passed through a chain, first a sender blacklist check, then maybe a keyword scanner, and finally a complex machine learning classifier. If it fails at any node, it's flagged. You also see this in automated troubleshooting wizards, sequential medical testing software, and graphical event handling frameworks, where a mouse click bubbles up through the UI layers. Sequential data passing is fundamental. But building these systems isn't just about linking objects blindly. Architects have to constantly balance competing priorities. Adding more nodes to a chain might increase the accuracy of your spam filter, sure, but it will directly impact performance by increasing processing time. Plus, it makes the overall system more complex to maintain. It is always a balancing act. Which brings us to Section 5, Advantages and Challenges, weighing the trade-offs. Because as with any architectural choice in software engineering, this pattern is not a silver bullet. Let's objectively weigh the pros and cons so you know exactly when to pull this out of your toolkit. On one hand, we get unmatched dynamic flexibility and deep decoupling of senders and receivers. That is huge. But on the flip side, that exact same decoupling introduces tricky debugging scenarios and the very real danger of unhandled requests mysteriously vanishing into the void. Let's expand on those advantages first. Because handlers focus solely on their own mechanism, your code adheres beautifully to the single responsibility principle. But here is the real superpower. The nodes of the chain can be added, removed, or completely shuffled dynamically at runtime. This massively improves high availability and disaster recovery configurations. If a specific processing node goes down, your system can dynamically reroute the chain to bypass the dead node without crashing the client application. That's a real game changer. But we absolutely must address the challenges. Because the sender fires and forgets, there is zero guarantee that a request will actually be handled, unless you've explicitly set up a catch-all receiver at the very end of the chain. And debugging? Yeah, it gets tricky because the execution path isn't strictly linear in the source code anymore. Furthermore, routing a request through 5 unnecessary handlers before it finds the right one creates real inefficiency. To mitigate this, developers have to aggressively set priorities and cleverly bypass handlers based on the meta information attached to the request. To wrap up this explainer, I want to leave you with a bit of a provocative thought. Look at the code base you're working on right now. In what real-world software scenarios could implementing a chain of responsibility be wildly more effective than maintaining those massive, fragile if-else conditional chains? The next time you find yourself groaning while writing a fifth else-if statement, ask yourself, is it time to build a chain instead? Thanks for joining me for this explainer, and keep building great software.